In this hour we will analyze the relation between the transfer function of an LTI circuit and its sinusoidal steady-state response. Okay, so suppose this is the block diagram of our LTI circuit from the input-output point of view. Okay, we have some input which we denote by X, and the output is represented, say, by Y. Okay, it's a linear circuit, and this input-output relationship can be represented, we know, by the transfer function, and let that be represented, denoted by H of S. Okay, now consider the following case, which is very important from the practical point of view. Suppose that the input is some sinusoidal function, okay, driving the circuit. So let therefore input be x of t as a cosine omega t plus phi. Okay, so this is a sinusoidal function with some amplitude a, phase phi, and frequency of oscillations being omega radians per second. Okay, this can be written as, using the trigonometric identity, this can be written as sum of a pure cosine and a pure sine in the following way: a times cosine omega t cosine phi minus sine omega t sine phi. Okay, and once we write it in this way, we can easily obtain x of s, the Laplace transform of our input. Okay, so this produces x of s equals a times cosine phi times the Laplace transform of cosine omega t, which is s over s squared plus omega squared, and likewise minus sine phi times the Laplace transform of sine omega t, which is omega over s squared plus omega squared. So let's write them down: cosine phi times s over s squared plus omega squared minus sine phi times omega over s squared plus omega squared. Okay, so this is x of s, and the transfer function is given h of s. Therefore, the Laplace transform of the response simply is h of s times x of s. Okay, therefore, y of s equals h of s times x of s, and that equals a cosine phi s minus sine phi omega over s squared plus omega squared. So we wrote these two terms in a single fraction. So that's our x of s, and that's being multiplied by the transfer function h of s. Okay, and this is the response for this sinusoidal input. Now this can be written as the following. So here we will have, there are two poles coming from the input, namely the pair at plus minus g omega, and then we will have the poles or the natural frequencies of the circuit, namely the poles of the transfer function. So let's write them separately. We have k over s minus j omega plus k conjugate over s plus j omega. Okay, so those are the terms due to input, therefore together they make the particular solution. And then we have the terms due to natural frequencies, k1 over s minus p1 plus k2 over s minus p2, Kn over S minus Pn. So these, as we said, are terms related to the input poles. Once again, the input is the sinusoidal function with frequency of oscillations omega. So that means poles, complex conjugate poles at plus minus j omega. Okay, so therefore these terms make the particular solution. And then the remaining terms are due to natural frequencies. Terms related to the natural frequencies of the circuit. Okay. Therefore, these terms make the homogeneous solution. So, if the circuit is stable, okay, so that means all the natural frequencies are with strictly negative real parts. The terms due to the natural frequencies, therefore, or the homogeneous solution, will decay to 0 as t goes to infinity. Okay. Circuit stable implies that homogeneous solution goes to 0 as t goes to infinity. Whereas the terms due to input, they correspond to sinusoidal, they correspond to sinusoidal function, sinusoidal signal, oscillating at frequency omega radians per second. Therefore, they're sustaining oscillations, they're not going anywhere, okay? They are there. And that part make the so-called steady state or the sinusoidal steady state solution, okay? So that means y of t converges to what we call the steady state solution. That is the solution when these terms are ignored, or when these terms or the time domain signals represented by these terms converge to 0. Okay. So that's called the sinusoidal steady state response. Okay. Namely, the particular solution. Okay. And now we will try to figure out this steady state solution in terms of the transfer function of the circuit. Okay. Now, the steady state solution, YSST, is the inverse Laplace transform of these two pieces, okay? Because inverse Laplace transforms of these terms, they will be all terms with something e to the multiplied by e to the let's say minus alpha t, alpha being positive, okay? And then as time goes to infinity, all those terms are decaying, and what will remain is what we're calling the steady state solution. So steady state solution, therefore, is the inverse Laplace transform of these two terms, and that equals k e to the j omega t plus k conjugate e to the minus j omega t. Okay, note that this and that, okay, they are complex conjugates of one another, which they must, because this function, this signal must be real, okay? And therefore this can be written as 2 times real part of k e to the j omega t. Okay, so 2 times real part of this guy, or 2 times real part of this guy. Since they're the complex conjugates of one another, the real parts are equal. Okay, therefore, if we figure out k, that residue corresponding to the pole of the input at the frequency at s equals j omega, then we will have obtained the steady state solution. Okay, so let's try to figure out what k is. So k equals, so this is the residue corresponding to the term or the pole at j omega. So y of s equals that. How we find the residue? We multiply both sides with s minus j omega, and then we evaluate ys times s minus j omega at s equals j omega. Okay, so let's do that. K equals ys times s minus j omega evaluated at s equals j omega, and ys is hs times x of s. Okay, so this is our y of s. That multiplied by s minus j omega, and then we evaluate that at s equals j omega. Now if you multiply this, which is y of s, by s minus j omega, note that this term is s minus j omega times s plus j omega. So that this term, s minus j omega, will cancel the s minus j omega that appears in the denominator, and the denominator becomes s plus j omega. Okay. So therefore what we have is that equals a okay, let me put it here. A times cosine phi s minus sine phi omega over s plus j omega, because the s minus j omega term in the denominator is cancelled by this term here that we are multiplying ys with, and times h of s. Okay, so this is this product y of s times s minus j omega, and then we're evaluating this at s equals j omega, and that will give us k. And once we have k, through this relation we easily obtain the steady state or the sinusoidal steady state solution YSST. Okay, so that equals a times cosine phi times j omega. Okay, s becomes j omega minus sine phi omega, and then you plug in s equals j omega here, so that makes j2 omega, and then here we have h of j omega. Okay, so that equals, now these omegas will cancel. Okay, and then we can write 1/2 times a. Okay, we take this 2 here, and what we have is cosine phi plus j minus sine phi divided by j. Okay, multiply both numerator and denominator by minus j, and that produces cosine phi plus j sine phi here times h j omega. Okay, now from Euler's identity we know that this is e to the j phi. Okay, so let's write it in that way, e to the j phi, and let's express h j omega in polar form. In other words, we have the magnitude of h j omega, that complex number, whatever it is, times e to the j, let's call it theta of omega, where the notation theta simply means the argument or the phase of this complex number h j omega, that is the transfer function evaluated at s equals j omega. And what omega was it's the frequency of oscillations of our input, which was a times cosine omega t plus phi. Okay, hence this thing can be simplified or expressed in polar form in a very simple way. What we have is 1/2 times A. Here we have e to the j phi, here we have e to the j something else. So we can combine them in a single exponential term, and that produces the following times e to the j phi plus theta omega. Okay, so therefore this is our K. A is coming from the input, it's the amplitude of oscillations. Omega is coming from the input, it's the frequency of, well, amplitude of the signal. And omega is coming from the input, it's the frequency of oscillations. Okay, and then theta is the phase of the transfer function evaluated at s equals j omega, and this is the magnitude of our transfer function evaluated at s equals j omega. Okay, now having figured out K, we can now try to write YSST or compute YSST steady state output steady state solution using this expression here. Okay, now we write the steady state output YSST equals 2 times real part of this, and this is K, so let's write it. YSST equals 2 times the real part of 1/2 times the amplitude of the input times the magnitude of the transfer function evaluated at j omega times e to the j phi plus theta omega, and that's being multiplied by e to the j omega t, e to the j omega t. Okay, now this 2 cancels this 1/2. A is a positive number, and well, it's real in any case, and h omega, the magnitude, is also a real number, therefore we can take it outside the real operator. Okay, and this can be written as a times the magnitude of the transfer function at j omega times the real part of e to the, now here we have e to the j something, here we have e to the j omega t, and those can be written as a single exponential. And then we have e to the j omega t plus phi plus theta omega. Okay, and then we know what the real part of that is simply using the Euler's identity. This produces cosine of this thing here. Therefore, the steady state solution for our circuit in terms of the transfer function is a times h j omega magnitude cosine omega t plus phi plus theta of omega, and theta of omega was the phase of h of j omega, phase of h of j omega. Okay, so that's a very neat expression of the steady state solution in terms of the transfer function. So let's write down here the very important conclusion that we have reached. Okay, suppose that we have a stable circuit. That is, all the natural frequencies are with strictly negative real parts. And for this LTI circuit, the transfer function is h of s. Okay, here we have the input, and here we have the output. Now, if you excite this circuit with a sinusoidal input, okay, with amplitude A, phase phi, and frequency of oscillations being omega, what you obtain at the output in steady state, because the homogeneous part of the solution will decay to zero very quickly, because we're dealing with a stable circuit, and what remains is the particular solution, and particular solution is the steady state solution, and that solution is YSST equals A times H j omega cosine omega t plus phi plus the phase of the transfer function computed at j omega. Okay, so if this is your input to your linear stable circuit with transfer function h of s, at the output you will see again a sinusoidal signal with the same frequency. Okay, and now how about the amplitude and phase of that sinusoidal signal? The amplitude will be such that it will be equal to the amplitude of the input times the magnitude of the transfer function evaluated at j omega, okay, s equals j omega. Omega is once again the frequency of oscillations. As for the phase of your input, output will be the phase of the input plus the phase of the transfer function, again evaluated at s equals j omega. Okay. Now let's apply this very neat observation to a simple example. Now, the impulse response of our circuit is given as follows. The impulse of some circuit is recorded as h of t equals 5,000 2e to the minus 1000t cosine 2000t minus e to the minus 1000t sine 2000t times unit step, okay, ut. So this is our h of t, the impulse response, Laplace transform of which is the transfer function. Now find for the circuit the sinusoidal steady state response. Okay, and our notation for that is y subscript ss t for the following sinusoidal inputs. Okay, a input is 5 cosine 1000t, so the frequency of oscillations, or omega, is 1000 radians per second, and in the second part the input is 5 cosine 3000t. This time the input also has a 45 degrees of phase. Okay, so the answer is here. All we have to do is compute h of s by taking the Laplace transform of h of t, and once we have h of s, we have to compute h j omega for omega equals 1000 and omega equals 3000. Okay, and from h j omega we get the magnitude and phase information, and that's all we need to write down the steady state solution, okay, that we see at the output for this circuit. Okay, so h of s Where is the solution? H of s equals 5,000 times the Laplace transform of this term, which is, okay, that's decaying oscillations. Okay, so what we have is 2 times s plus 1000 over s plus 1000 square plus omega square, and omega is 2000. Okay, 2000 square. And here we have the sine term, that's minus omega over s plus 1000 square plus omega square. So omega is 2000, right, over the same denominator, omega square. Okay, and written as a single fraction that produces 10 to the 4s over s squared plus 2000s plus 5 million. Okay, so that's our transfer function, h of s. So let's compute h of j omega at omega 1000 and also omega 3000. Okay, omega equals 1000 radians per second. Okay, so that produces h of s evaluated at s equals j 1000, and that equals j 10 to the 7 minus 10 to the 6 plus j2 times million plus 5 million. Okay. Now, from which we see h of j 1000 equals j10 over 4 plus j2, and that further can be simplified into 1 plus j2. So this is the value of our transfer function h of s evaluated at s equals j1000. Okay, why j1000? Because we're trying to figure out the steady state solution for this input, and for this input the omega is 1000. Okay, that's why we're evaluating h of s at j omega, j1000. So this is the transfer function evaluated at that particular frequency, and so all we have to do is figure out its magnitude and phase. The magnitude is square root of 5, the phase is arctangent 2, and that's what we need. So since the magnitude is square root of 5, at the output what you will see is the amplitude of the input times that magnitude, which is square root of 5. As for the phase, the output will be such that cosine, it will be equal to 5 square root of 5, okay, times cosine omega t, in this case 1000 t, plus the phase of j omega, which is arctangent 2. Okay, so the magnitude equals the magnitude of 1 plus j2, which is 1 plus 2 square divided, and then you take the square root, that produces square root of 5. And the phase of j1000 is the phase of 1 plus j2, which is arctangent 2 over 1. Okay, arctangent 2. Therefore, the steady state solution is, you take the magnitude or amplitude of the input. It's 5. You scale it with the magnitude here, the magnitude of the transfer function, which is square root of 5. Okay, so this is the amplitude of your sinusoidal steady state solution. And how about the frequency of the steady state solution? The frequency of the steady state solution is the same as the frequency of the input, which is 1000 radians per second. And as for the phase of the steady state solution is you take the phase of the input, which in this case is 0, plus you have the phase of the transfer function. Evaluate that, j omega. Okay, so phase is 0 plus that thing, hence it's arctangent 2. And that's your steady state solution. Okay, let's also do quickly the second case for the second input. This time we're going to evaluate the transfer. We're going to evaluate the amplitude and, the magnitude and the phase of the transfer function at J3000. So J3000 can be computed to equal 15 over 13 times 3 minus J2. Okay, and that produces the following magnitude. That equals 15 over square root of 13. So that's the magnitude of this complex number. And the phases J3000. The phase is arctangent minus arctangent 2 over 3. Minus arctangent 2 over 3. Okay, therefore the steady state solution is you take the amplitude of the input, which is 5, you scale it with 15 over square root of 13, so that makes 75 over square root of 13 cosine. The frequency is 3000, so the frequency of the output is also 3000. The phase is, you take the phase of the input, which is 45 degrees, or pi over 4 radians. To that you add this phase here, which you obtained by computing, by using the transfer function, minus arc tangent 2/3. And that's your steady state output.